Let's look at question 16. In right triangles, ABC and RST, looks like they're running out of three-letter words. All the other vertices of all the other shapes added up to like different words. There was dog and cat earlier, but this is just plain old ABC and RST. They're telling us they're right triangles, so the longest side is called the hypotenuse, the one opposite 90 degrees. That's what right means. And that's 4 on the smaller one, and the hypotenuse on the bigger one is 16. So if these two triangles are similar to one another, then 1 to 16 is the ratio of the corresponding what? Okay, let's try it. Let us draw these triangles out and see what happens. So let's go ahead and say that this right there is our first one. And let's make that the bigger one. Okay, so let's label it. They said AB is the hypotenuse, so I'm going to be careful to make sure AB really is the hypotenuse. That would make that C. That's 4. And then RS is the hypotenuse over here. That's 16, making this T. So I'm looking at it, and I'm seeing that in order to go from smaller to bigger, I'm multiplying by times 4. It goes up by a factor of times 4. And these are one-dimensional values, right? Because the number 4, the number 16, these are just one-dimensional distances from A to B. It's just a side length. And it has a scale factor of times 4 to go from ABC to RST. So it would be times 4 to go from AC to RT as well. But look at the answer choices. Now, if you didn't know the rule that I'm about to show you, you can still figure this out by putting together a couple more concrete numbers into position, and then you would actually find the area of these triangles. You could do that. The area of any triangle is 1/2 base times height. You see that on the reference sheet, and then you can go for it. You can actually test answer choice 2, which suggests that the areas would be the same. You would not even think to test the volumes because these are two-dimensional shapes. They said the word triangle. Triangles have 0 volume. It's only 2D. It doesn't have that third dimension, no thickness to it to give it a volume. You wouldn't be that interested in answer choice 1 because we can already tell from just the 4 and the 16 that that's a scale factor of 1 to 4. It has a ratio of 1 to 4, not 1 to 16. So what would give it a scale factor of 1 to 16? If you had made some of these concrete choices and plugged in some numbers that actually work using the Pythagorean theorem for the legs of these two triangles, you would find that the perimeters don't have a 1 to 16 ratio. And you didn't even need to do that again because still AB and RS are side lengths. Those are components of the perimeter and they have a 1 to 4 ratio relationship. So just using basic logic, we've already broken it down to answer choice 2. But I do want to teach you a rule to help that's actually pretty cool in geometry, and it goes something like this. If you are going from simpler one-dimensional values to more complicated two-dimensional values, and even to three-dimensional volumes, there is a relationship between that. So if the sides go up by times 4, it'll be the one-dimensional value times 4 squared to become 2D, and it'll be the one-dimensional value times 4 cubed to give you the ratio of the volumes. So you could think of it like this. If this is the one-dimensional value, or scale factor rather, you take that 1D and you square it to get 2D. You take that 1D and you cube it to get the 3D answer. It makes sense. It's just not typically thought of this way, but now you can think about it that way. So let's go ahead and try that highlighted row. So if the 1D ratio is 1 to 4 times 4, then the 2D, the volume, or sorry, the 2D, the area would be 4 squared, which is 16. So that confirms answer choice 2 is correct on this one. And then the volumes would be 4 cubed. So that's already bigger than 16. So 1 to 16 is just the ratio of the area. So what does that really mean, practically speaking? That means that if we went ahead and actually found the area of this larger RS that has one-dimensional values that are 4 times larger than the smaller triangle ABC, then RST would have an area that's 16 times bigger than triangle ABC. That's what that means. Now, I've never seen this rule being applied in the way I'm about to show you on a Regents test, but just so you understand it, it does come up on the ACT and sometimes on the SAT. What if I had a couple other shapes? Let's say we had 2 different triangles. Here's one. And here's another one. They are similar triangles, just like in the previous one. I'm just trying to get it to generate the straight lines. There we go. So what if I told you that the actual area of, what if I just give you the areas? I'll give you the areas of the triangles, and maybe you'll have to tell me something about the side lengths instead. So we'll work backwards. So in our example question here, our follow-up question, let's say that this larger triangle has an area of 36. And the smaller one has an area of 12. 12 square centimeters, or 12 centimeters squared, whatever kind of units you like. So these are 2-dimensional areas. I'm giving you the 2D value. So let's put that in our table, or let's figure out what to put in the table first. So what we know is that in order to go from the smaller one to the larger one, we're going up by a scale factor of times 3. So times 3 is what goes in the 2D column here of our table, times 3. So what would be, if the larger triangle is 3 times as large, if the area of the larger triangle is 3 times the area of the smaller one, by what scale factor are the side lengths? What's the ratio between the side lengths? So what we would have to do, if that times 3 equals 1D squared, then we'd have to go ahead and take the square root of both sides to get 1D relationship by itself. So that would mean that root 3 would be the relationship between the one-dimensional sides. It would be 1 to root 3. You know, root 3 is a number. All right, so that's how we work backwards. If they had given us the 2-dimensional relationship, we could have squared it to find the 1-dimensional relationship. If they had given us the 3-dimensional relationship, we could have cubed it to get the 1-dimensional relationship, and then we could have squared it to get the 2-dimensional relationship. Just know that it's the 1-dimensional relationship inside of the squared and the cubed in the 2D and 3D columns, respectively.